There we go. We are being recorded. So, welcome everyone. I think maybe, okay, I need to change something about my screen sharing. Okay, what did I do? Screen sharing, stop. I will only share a tab because if I do that, then I can see you and see the tab at the same time. Let's see. Yay, there we go. Ooh. All right, so first warning, it's being recorded. I guess this is quite normal these days. The recordings are going to show up on a website, but I think they're going to be in the Drive folder, which is only accessible if you are at the university or something like that. So, welcome everyone. This is CMP 653, Theoretical Foundations of Reinforcement Learning. And we're gonna do introductions today. Here's the contents. So we start with Miss Trivia, some introductions about myself and the course, some discussion of the structure of the course, the format of the course, how the grading is going to work. You may ask your questions if you have any at this stage about it, and then I do a little bit of expectation management there as well, and I think that's important. And then we'll talk a little bit about reinforcement learning today, not too much, just very high level about what is reinforcement learning, what is this MDP framework that we're gonna use during the whole semester, and a few words about these pesky probabilities as well. So who is this guy? So my name is Csaba, and if you're wondering how to say my name, the Hungarian spelling is going to be very confusing. You probably want to look at this other spelling and then you'll be pretty close. So you can just call me Csaba. Okay, that's very, very simple. And so I live in Edmonton here, as you might have guessed, a big family, happily married with my wife, 4 kids, spouses, grandkids, everything. I have been born in Hungary, so this map shows you where I've been. Oh, do you see my cursor? Oh yeah, you see it. But I grew up in Hungary, somewhere in Europe, there, in the eastern part of it, a little village first, and then a bigger city, and an even bigger city, even bigger city. Eventually, I moved to Canada. That was in 2006. And just very recently, I had an adventure in Europe again, in DeepMind in London. That was in 2017. So from 2017, I'm also at DeepMind, and I'm only part-time at the university. And I came back in 2019 to enjoy family, friends, and this lovely climate here in Edmonton. And since I'm here again, and I like outdoor stuff like skiing, biking, oh, even running and rock climbing, if you didn't know that before. So in terms of work, I did my PhD back in Hungary. at the University of Szeged, which is in the south part of that tiny, tiny, tiny country. And that was back in 1999, where reinforcement learning was not that cool, although I thought that it was super cool. So to me, it was always very cool. Just not many people seemed to care that much about it at the time, although the whole community was, machine learning community was much smaller. During my PhD, I started working for this company, MindMaker, which was a US-based company, and I stayed there until 2002. I had the research position basically there, so it was very nice. In a way, it was similar to DeepMind. It's kind of like mind. It started with some mind, now it ends with some mind, and then deep is added to that. But it's kind of the same story. MindMaker was not as big as DeepMind, but it was fairly big. And around 2002, I left MindMaker and I joined a Hungarian research institution. You can't say its name. It's MTA Stocky or MTO Stocky. We would say it Hungarian. And I was staying there and I was leading their machine learning group and I had a great time. And then around 2006, I moved to the U of A and then the rest you know. So since then, I'm basically here with that 2-year break at London. And in terms of research from the early days on, well, it kind of doesn't say, but well, I guess I was interested in like how thinking and the brain works, but I very quickly figured that biology is just not for me. I don't like to work too hard, very lazy person. So I didn't want to memorize a lot of things. And yeah, I figured that biology is to a large degree about that. And I was more interested in, the working mechanisms, the principles. So I ended up doing math and CS at the same time, but mainly math, because I somehow thought that, wow, the way you figure out what the brain does is that you're kind of thinking about the algorithms and the math underlying the brain. And so early on, I discovered reinforcement learning. I was really fascinated by it, and I said that this is the best framework to think about the mind and how thinking works, and how to create, I don't know, intelligent entities, agents, if you wish. And I also discovered that people in other disciplines like control have also been thinking about this, and I made some friends in control. So I was working a little bit on adaptive control that resulted in a book about adaptive control at the time. It's been very early ages. Later on, when I got back here, I saw that maybe for the course that I was teaching at the time, it would be nice to have some short summary. So I wrote this small ARIA book, which is only 100 pages long, which was more like a mixture of an undergraduate/graduate level take on RL, so nothing really heavy in there. And in terms of theory, it takes kind of a theory viewpoint, but it doesn't quite give you the terms. I told you that I'm lazy, so writing terms is hard because you have to think about the conditions and it has to be correct. If you write that this is a theorem, it better be correct. So I was just writing words, and so this book is it's a short book. I think it's good for certain things, but I think maybe it's a little bit dated too. But I can still recommend it. It's a nice book. More recently, I wrote a second book that we're going to refer to quite a bit in this class, and that's the Bandit book. So the Bandit book is based on a class I was teaching here a while ago. And it was like this class with enthusiastic people, and me teaching it a couple of times and writing lecture notes. And then eventually we turned those into a book with Theorem, and it was published, I think, a year ago. Well, 2 years ago by now. It's 2022. And so that kind of that book covers some aspect of reinforcement learning, but well, of course, it's not really focused on reinforcement learning, but it covers some foundations that are super useful for reinforcement learning as well. Reinforcement learning is like the big brother of bandits, so it's just bigger, more complicated. So knowing that book cannot hurt, and it's free. You can just download it from my webpage, the PDF. I mean, it's like I can't give you free printed copies, and unlimited numbers. Unfortunately, I'm not getting those. Anyways, so that's the Bandit book. So to answer Vlad's question, am I going to teach the Bandit course again? I don't know. Like, if I get tired of teaching this course, then maybe. There is new stuff that's coming out. It's scary. Like, it's a thick book. Where is it? If you haven't seen it, this is the book. This is how thick it is, and I think it's too big. It's like it's hard to carry it with yourself if you go on a trip because it's too heavy. I wanted it to be smaller, and it's missing so much, even of bandits. So it's pretty amazing how much knowledge people generated about bandits. Anyways, in terms of research, I've been working basic stuff on Areal at the beginning in the 90s. The name of the game was convergence, almost sure convergence in the limit in some sense, maybe some convergence rates. And when I got here, I kind of got really interested in finite time analysis. So getting rid of the asymptotics and then being a little bit more careful about how you do your analysis. And also the other aspects that I picked up was to deal with functional approximation, so RL and generalization. A lot of the work that we were doing with my group after I got here were revolving around that topic. And later on, I started to pick up exploration as something that's really unique to reinforcement learning. And then that diverted my attention to bandits, which is the smallest example where this exploitation dilemma, which you may have heard about, comes up for the first time. So I saw that it is nice to investigate this in its purest form, because then you can maybe distill more knowledge about it. And then, so I've been working on this problem for quite some time. That resulted in that book. And it seems to be true. So these days we see a lot of the other algorithms are borrowing the tools and the techniques from the bandit literature. So I think it was a good bet in retrospect. And I partially have to thank Rich for that, because he kept me asking Rich on that. Well, what is really special about RL? You should be working on what's special about RL. You should think about that. And I figured it's exploration. All right, so that's about me. I don't know, do you have any questions? Okay, no questions. Now let's move on. So here we see our two lovely TAs, where I was online, Alex and Vlad. They can wave their hands. Hey. By the way, I really do appreciate if you keep your camera on. I think it makes for a much better experience for everyone involved. Last but not least, yours truly really enjoys when they can see people and you're not just talking to a screen. So thanks for turning on your cameras if you're doing that. So the course comes with two websites, the EClass website and the True website. And the True website is a revamp of the website that we used last year for the course with some new content and some changes. And that's the main website that we're going to use. So let me switch there. You don't see that. I have to stop sharing and then share again. Oh, maybe I can, okay, I can share the window and that will still work. Yes, good. All right, awesome. So this is the website. If you didn't come across it, let me tell you a little bit about it. So on the right, you see these menus, and these are the lecture notes that were made for the 2021 edition of the class. The current lecture notes are gonna sit here. For now, we just copied over everything that we had before, but there could be some changes. So in general, this will be updated and the old lecture notes will stop to be updated. Apart from that, there is this homepage that just has this fun graphics on it. And then there is the About page, which explains what the course is about. We'll talk about that a little bit later. The Prereqs. And so in terms of the Prereqs, I'm suggesting that you look at these chapters of the Bandit Algorithms book. So you can access it, the book directly here. It's 596 pages. Good, but you don't have to read the whole thing. Chapters 2, 3, 5, 7, 26. What are those? Chapter, okay, 1, you can skip that just like bandits. 2, that's foundations of probability. So that's a very short summary of the notation and the basic results of probability theory that we're gonna need. And you should definitely look at this. So if you haven't seen measure theoretic probability, then you definitely want to read this because I'm going to use this notation. And the reason is not because I want to be fancy or anything, but just this notation is something that people agreed on, and everything is very clearly and cleanly defined, as opposed to the notation that you see today, unfortunately, in many of the research papers, where things are not clearly defined and you need to guess the meaning of everything. So we're gonna stick to this notation, and it's also worthwhile to try to understand conceptually why you want to do this measure theoretic approach to probability. So I think that it's a good opportunity for you to just learn about this. The things that we need, the results that we're gonna need are not very difficult, and they're all included in this chapter and the next chapter. So the next chapter, that's chapter 3, That's about stochastic processes and Markov chains. And here in this class, we're going to talk about more complicated things than Markov chains, but not much more complicated things. And so for this, it's important to understand what are Markov chains and how do you define them? And so this is what is being done here in this chapter. So these are the first two chapters, chapter 2 and 3. And then there is 5 and 7. So 5 is about concentration of measure. You don't need concentration of measure up until kind of the middle of the course. So at one point, I'm going to say, oh, this is true because of, I don't know, Hoeffding's inequality. And everything that you need to know for taking this course about concentration of measure is going to be included in this chapter. And if need anything else, then I would just introduce that, but I don't think that you need anything else. So you probably have heard about the central limit theorem. So this concentration of measure, if it sounds something very unfamiliar, it is just almost like the central limit theorem. It's still talking about that if you have random variables which are nicely behaving, then if you take averages of these random variables, then the averages, well, they're going to concentrate around their mean, and the distribution of the average is going to be close to a Gaussian distribution, right? So the central limit theorem very nicely lays this out. And if you wish, the concentration of measure inequalities are refining this so that you can have a much more precise understanding of how quickly this convergence in distribution to the normal distribution happens. And because the central limit theorem just says, if you remember that if you have the averages of this, let's say, independent random variables which are a common mean, then the average recentered around 0 converge and normalized using, let's say they have common variance that normalized with the standard deviation converges to the standard normal distribution in the limit. But it doesn't tell you, well, how big deviations you can expect from the mean. So the average, it's a random variable, it deviates from the mean, and like how big these deviations can be. So concentration of measure just very precisely talks about these deviations. The probability of exceeding a certain threshold above the mean or below the mean, like what is that probability? How big is that probability? Putting bounds on this probability, that's concentration of measure. And the way it relates to the central limit theorem is that the central limit theorem just says that, well, in the limit, everything is Gaussian. And here, everything is like, okay, it's not the limit, so it's not yet Gaussian, but it's close to Gaussian. So it's like how close things are to Gaussianity. So this is what concentration of measure is about, at least for us, for the purpose of this class. And so chapter 5 is gonna cover that. Which chapter was the next one? 7. Oh, the upper confidence bound algorithm. That's not important until the very end of the course. At the very end of the course, when we're talking about online learning in RL, you may want to read this, but I will remind you that. And 26, so the 8. So 26 foundations of convex analysis, that's going to be a fun read if you haven't met convex analysis yet. We're going to talk about the mirror descent algorithm. And for that, it's good to understand a little bit about convexity, not too deeply, but we probably don't need as much as you can see here. So this is way more than what we need. We just need the mirror descent analysis, which is in chapter 28. And if you look at that analysis, it's pretty elementary. But
Yeah,
some basic things about convexity are going to be needed. Yes?
I was just gonna say, you definitely get to look at Jensen's
Yeah, yeah.
inequality.
Yeah. Jensen's inequality is like the bread and butter. It's the, I don't know, the the only inequality that you need to remember if you wish. Well, some people would say Cauchy-Schwarz, but it's kind of the same thing. Um, so Jensen's inequality definitely. Bregman, Legendre, it's not too important. Optimization is maybe more important. Projections, not too important. Okay. And then 38, that will be the obvious chapter. That's about Markov decision processes. And at the end of the course, we are going to cover the material in this chapter to some degree and more. This chapter very precisely defines what we mean by Markov decision processes and policies, optimality equation, and so on and so forth for the average reward case. So most of the course is going to be about the finite horizon case or the discounted case. And if these words do not mean to you anything, don't worry, it's okay. But this chapter, you can use, you can read the definitions and like things up to finding an optimal policy during the first couple of weeks of this course and try to understand what's going on there. The rest, learning in MDPs and this upper confidence bound for reinforcement learning, they're not needed until the very end. Okay. So just the very beginning. All right, so that covers this. And then there is this other book that I recommend. There are some chapters there, but I won't go over that. This is my book. Is it still working? Yes, it's working. Yeah, I mean, I don't know. It's optional, I think. The Wikipedia page on Banach's fixed point theorem, you should read that. It's pretty good. It was pretty good when I wrote this comment about that. It was pretty good. It still looks good. It's pretty short. You can see that that is a theorem statement. For Wikipedia, that's an achievement. Sometimes it's pretty fuzzy. And there is a proof, and the proof was correct at the time I looked at it, and I hope that it's still correct. No one should. Hopefully they didn't edit it. Okay. All right. Nothing really happened. Okay. All right. So we talked about us. Lecture time, you know, when the lecture time is going to be. So the first 3 weeks of the course will be online because the university doesn't let us meet in person. And the format during this first 3 weeks is going to be flipped classes because we do have the recordings and the lecture notes from last year. I just didn't see much of a point, and I also got the feedback that from the learning experience point of view, if it's an online course, then it's better to have this flipped class. So we're gonna go with the flipped class. So what does it mean? Before the class, you're given this reading and watching assignments, which is to watch the lecture for the next lecture and read the associated lecture notes. and look at the whiteboard notes, and then come to class when you have already done that. And then the question is, what are we going to do in class? Well, I will give you a short summary, a short take on the contents that shouldn't take up much time. And after that, supposedly we're going to have some fun discussion about the topic. You will have some questions. And regarding that, so as part of assignment 1 at least, the last question on assignment 1 is going to ask you to ask questions for the upcoming lectures, a certain number of them, and for every lecture, you should be voting on other people's or your own question. You will do this on Slack. On Slack, we will have this Slack channel. This is going to be on this discussion Slack channel. We'll create this thread and it will be obvious, all the discussion surrounding what's happening in the class and what you need to do and so on and so forth. This will happen on Slack. So you should, if you're still not on Slack, then you should email your TAs. They can put you on Slack. And then you need to join these two channels. And so for the questions, you will ask the questions there on Slack, and then I will answer the most popular questions at least, and then we're going to have some discussions. That's how it's going to be for the first 3 weeks. After that, the university is going to decide whether we are in person or not. If we are in person, we go back to the standard mode, which would be to be in the classroom, and I will be at the whiteboard or blackboard, whatever it is going to be, and do a normal lecture, which normally is highly interactive. So students are keep asking questions and pushing around the lecture the way they need it. So that's the plan for now. If the university doesn't let us to meet in person, then we're going to continue with this flip class setup. Okay. So on EClass, the EClass is just a stem. We are going to use it just for announcements and discussion. Sorry, we will not use it for announcement and discussions. For this, we will use Slack. We only use it for assignment submissions. Discussions are going to go on generally on the Slack channel. You're encouraged to ask your questions. There are no stupid questions. If you have a question, you're wondering whether you should ask it, you should ask it, because other people are going to have a lot of questions. And I ask a lot of questions that maybe are naive and whatnot, but I mean, things are working much better if you ask a question and you get a fast answer, and there's no shame in asking questions. It's just ask questions, be brave. It's good. It's all good. I much prefer people asking any sort of questions than people not asking questions and then maybe later complaining that, oh, I didn't know this or I didn't know that. Just ask questions. Nothing bad can come out of it. Okay. The Google Meet information. So we're going to keep using this Meet link. So and this invitation. Hopefully, it will work well for us. For grading policies such as like late submissions and so on and so forth, refer to EClass is the standard department policy that I'm mostly using. So there is nothing really special about that. Just don't be late. You're gonna be have plenty of time to submit your assignments. Try not to be late. So we already talked about the lecture notes, the flip class. Okay, so here are the lectures. This is how it looks like now. So these are lecture videos, and if you click on the discussion, that's what's happening now. But since this is not recorded yet, the recording hasn't finished yet. Oh, what? No. Okay, so this is a fake link. This is going to go to this video once it's recorded and uploaded. And this is just the lecture video, and they're whiteboard notes. And maybe here it's not whiteboard, but slides, but it doesn't matter. So you'll get the slides. Oh, by the way, you could just get the slides now. I think could be useful. All right. Anyone with the link? Okay. All right. So here are the slides. So I see that there was a question. I missed that question earlier. Kushag asked, are there solutions or hints available for the exercises in the Bandit book? So hints can be available from your TAs and me or on the Slack channel. Just ask questions about that. The solutions are straight available, but I would discourage people from just looking up solutions. But okay, not for every exercise, but for the exercises that are a little bit more challenging that I written up. And if needed, then I can share the PDF with people. Well, I'm not, well, or at least parts of the solutions. Like if needed, then we can share some solutions. We can discuss it. All right, going back. So right, so we discussed all of this. So this is last year's, and then so when I say there is an assignment to watch the next lecture, then you just watch this lecture. Hopefully it's not too painful. You can always speed it up. About the work you do, everyone's itching to know about that. There's going to be 4 assignments. There is a zeros assignment by tradition in this class. So that is mostly for self-assessing whether you're ready to take this class. So these type of questions, the questions that come up on this assignment, they do not require, like advanced math or anything, but they require some familiarity of, like thinking about these proofs and writing up proofs and formal reasoning, which we're going to do a lot in this class. I'm going to do that a lot. And also in the assignments, you're going to be asked to do similar things. So this is just for self-assessment. You will still submit them so that we also see what you did, but you don't get marks for assignment 0. Okay, Alex?
Oh, I was just gonna say, for some of these questions, there's no one way to prove them. Like there may be a proof we come up with, but maybe you find an easier proof.
Sure. Yeah,
You can
it's
do
like
that. Yeah. So.
for many of these questions, yeah, like if it's a solution, it's a solution. Any solution goes. Yeah. True.
Sometimes the hints are helpful. Maybe you may not find them helpful. So it's just like a
Oh,
heads up.
okay.
Yeah.
So that's what you mean. That's good. Right. Yeah. Like don't even look at the hint maybe before you start to think. So start to think about the answer to the question, and then if after, I don't know, like some struggle, you didn't make any progress on answering the question, then maybe look at the hint. But try to struggle. Like life is about struggle. Struggle is good. That's how we get strong. Okay. So here are the deadlines. Generally, you have 2 weeks and so on so forth. If someone has any concerns about any of these deadlines, the earliest you contact me, the better. These are all up for discussion to the limit that, like, okay, we are like it's publicly announced now, so it's kind of like yeah, everyone sort of have to agree if you want to change the deadline. So that if we need to change some of these deadlines, then there will be some voting process. And I was told by the university that I cannot change these announced deadlines unless everyone agrees. So it's like, it does work in smaller classes. In bigger classes, it doesn't necessarily work. But if we made some mistake, or like, yeah, like if there is a reasonable argument to be made of why anything should be changed, let us know. So class participation marks, so this is about the questions and the voting. So part of assignment 1 is going to be that you need to ask questions. And thread will be created on Slack 5 days before the class. Then you have to ask these questions, and then you have to do the voting. It will be pretty clear and obvious once this is happening of how to do that. So there is also a course project that has like 3 parts to it, if you wish. A proposal, which is due on the 7th of March. There will be presentations in the last 2 classes where all the people who were doing their projects are going to present the results. And there is also a report which is due a little bit later. And you get marks for all of these. And so regarding the marking, it's somehow on EClass, I think. There is like the distribution of the marks. I forgot where it was. We should copy it.
I think it's in the outline, course outline.
Is it in the course outline?
I think we put something there, maybe.
It was there. Yeah, okay. That would be, yeah, okay. It's just not so visible. All right, that's it. So 4 assignments, each worth 10% of the mark, take home midterm, 20% of the mark. There will be a project for the remaining for 40% of the mark. And yeah, so regarding of working together, here are some policies. So on the assignments, you should work alone. For the projects, you can choose to work in pairs or work alone. We'll see how many people are going to take the course for credit at the end. Maybe I will nudge people to work in pairs if we have too many people taking course for credit, so that we won't have enough time to cover that many presentations in class. So then maybe we will need to have a third day or something. We'll need to figure that out. And you can, of course, talk to others. You got an assignment and then you want to discuss ideas and whatnot, bounce around ideas. That's fine. You can take notes during those times, but like you shouldn't write each other's like solutions and whatnot. It's just like common sense that you're here to learn. And that would not help you to learn if someone else would be solving your problems. These problems are for you. So Kenneth is asking whether the assignment discussion should be on a private channel. You can ask, and you should ask, I would say that ask the questions on a general channel. I prefer that. It could be other people who can answer those questions. So it may not be Vlad, Alex, or me. Could be others who are just on a public channel and they are very enthusiastic and then want to give answers. And so I think it's good. So on a general, so the difference between a general and a private channel is that on a private channel, we want to discuss things that are related to, maybe grading or like deadlines that are not of a concern for the students who are auditing the course. But even students who are auditing the course may want to see those questions, right? So that's the difference between these two channels. That's the intent. Okay. Oh, here I have some reference to a book that you can read on your own time. We are not really going to use that many results from here, but it's a nice piece of work, so I can recommend that you do look at that too. All right. So regarding topics, I think I'm going to post a bunch of papers that came out during the last year or so, which are papers worthy of reading. Okay. In general, in the projects, I expect you to read and understand and distill results from papers, and then maybe synthesize a bunch of papers together, but not too many. It's not, we don't want to be too ambitious. It's like a smaller piece, better done, is better than a bigger piece, which is not that well done, in my opinion. So even if you just go for one paper and try to understand it, usually there is a lot of context around that paper. And if you're rewriting the paper with your own notation, make it better, make it nicer, that is a good project in my mind. If you do something like on the top of it, like usually these papers do have a bunch of open questions in them. If you're ambitious, you can go after any of these open questions, or you can come up with open questions on your own, or just during the class, there will be a lot of open questions mentioned, and you can try to come up with solutions for those. Those are all good project teams. But the minimum expectation is that you read the research paper and then you just make it much nicer. If you are, Alex? No? Okay. Just fixing there. Okay. All right, and so here I'm a little advertisement that we have this area theory virtual seminars. No seminars scheduled for now, but they're gonna come back in February. So we're taking a little winter break here. But these are the seminars we were running, and you can look at the past seminars we've been on since 2020 spring. So there's a lot of talks, a lot of interesting theory papers. This is all theory papers. These papers are all appropriate for the purpose of this course. Some of these may be outdated because the field is moving quite fast, but otherwise it's very good. All right. So back to my presentation.
I think there's a question in the chat from a couple minutes
sorry.
ago.
Yeah. Okay. Thank you. Okay, so Prabhat is asking how is this other course differs from mine? I think everyone has their own spin on things. The way I'm trying to think about the material I'm teaching, okay, so first of all, it should be something I know of. So I can't really talk about things I don't know of. I think that that's the same for them. So their material is going to be geared towards things that they did. My material is geared towards things I did a little bit. So that's one point. But for me, the other thing that is important is I'm trying to teach things that maybe, just maybe, have a chance of withstanding the test of time. Meaning that I try to teach results that maybe not going to change in the future. And so if you learn about these results, then they're just gonna be with you, and they're gonna be like, like a result to remember, which is an important result in a way, right? So like a lot of times research is evolving, and then it's developing in many different ways. And at any given point in time in this field, there's zillions of little tentacles that are growing in every direction. And most of them are unfinished results in the sense that they don't feel complete. They're like, you know that something is missing. But occasionally, you know that like, okay, this was a very nice question. It's focused on a question that is a very nice question. And we got the results right about this question. Maybe we don't have the proof from the book yet, but at least the answer to the question is seems to be the final answer to the question. So I'm trying to gear the topics that I'm covering in this class towards questions for which we know the final or near final answer. And so that kind of also pushes me back a little bit because current research obviously looks more like the other type where you have unfinished results. And so we're going to talk about, although most of the results that we're going to cover are results from last couple of years too. So it's like, it's not even true. But this is my bias. I'm trying to tell you about questions for which we know the final answers to. Or maybe we almost know the final answer. Well, we know the final answer to some degree. And in their case, I think that it's a lot of times they love methods. So that's one difference. I like questions, which are nice questions, and they love methods. So they will be talking about, oh, this method or that method, what are the properties of this method? So this algorithm-focused analysis. And I try to focus on the questions. Hopefully this is going to be a little bit more clear. So Alex is saying that, okay, not as philosophically as me, but that the other course generally focuses more on regret bounds, exploration, optimization, and policy gradients. So these are the topics, you see, but this is, yeah. And we will mainly focus on planning with some discussion on batch RL and online RL. Yeah, you could say this. To me, the focus on regret bounds and exploration, well, that's kind of this would be the same, right? And then again, like you want some final answers and to some questions there. So I think that we're gonna get there in online learning and exploration as well. So for the questions for which we know the answers, to get the results, the best way seems to be to look at planning. Because if you develop your results for planning, and the simulation optimization kind of thing, then the rest follows almost trivially. Not quite, but there are some twists, and sometimes because of those twists, we don't know the answer. But yeah, a lot of the action is going to be on planning, but it's not because I like planning, but it's not just because I like planning, but it's because I think that by studying planning, you learn all the tools and techniques almost all the tools and techniques that you need to solve these other problems, almost all of them. So it's almost sufficient to study planning. Okay, anyways, slideshow. No, it's not how it works, okay. Present meeting. No. Okay, so I think we covered everything that's on this slide. So now about the philosophy of the course. We already talked a little bit about philosophy, but well, you're here, so that's great. But you may still be wondering about like, okay, why do we care about theory that much? Maybe teaching the core now, but I said that maybe it's good to explain a few things about this, the foundations. And so to me, theory means math. It doesn't mean theorizing about things like, like making assumptions about the world. So to me, theory is just math. It's just like doing math. It just, what math is. It's just like you have some bunch of rules and you have some axioms, and then you derive conclusions based on that. And so that's what doing theory means to me. At the same time, I'm using theory as a thinking tool, and there you could say that, well, that's theorizing, maybe. So I like to use theory as a thinking tool to think about the problems I want to solve, or I want computers to solve. And if you think about it, that's always have been the case in CS. So it's kind of weird if people are not doing that, right? So right from the beginning, when people realize that, well, okay, what are algorithms? Okay, we can define, like rigorously what algorithms do mean. Then they realize that we also need to be able to say things about these algorithms. We need to be able to say that the algorithm is correct, it's sound. We have to be able to say how long does it take for this algorithm to run on this input, right? So there is no difference to this if you're talking about learning algorithms, right? So we still want to be able to say that, hey, my algorithm is sound, right? If the input that the algorithm is fed with, or the data that the algorithm is meeting, or the environment that the algorithm is interacting with, is such and such, then I can expect this algorithm to produce results of this and that quality. And it's almost weird to try to do anything without doing this sort of work to me, right? Like, so you're developing algorithms and then you don't know what they're good for. Like, how do you know that an algorithm is gonna work? Well, to me, the ultimate way of knowing is proving that, okay, maybe it's on some narrower set of conditions, but at least in those cases, my algorithm is going to work. So that's, I think that theory is a way of generating knowledge that is irreplaceable with any other means. So this doesn't mean that this is the only way to generate knowledge, but it's sort of like the only way to generate hard knowledge. Let's put it this way. So hard knowledge is like yes or no. It's not like, oh, maybe, sometimes, or possibly. That's kind of like intuition, some soft knowledge. That's also good. It can lead to good things. But to me, hard knowledge is pretty important because then you can build on it, right? So that's what we do a lot. We want to have reliable things, reliable algorithms. And how do you get reliable algorithms? Well, if you can prove that they are reliable, then they are reliable. Otherwise, I don't know. So that's why. The other thing to note is that to me, theory is always about these questions about algorithms. So it's the question of whether an algorithm exists with certain properties. So the algorithm should be able to, like multiply matrices of, I don't know, any size, and like how long does it take to do that? How much memory do you need to be able to do that? The questions are the same for learning algorithms, pretty much, with some variations. And what's again very beautiful about theory, the way of doing it this way with math, is that sometimes the answer is going to be no, right? So that's really unique. So sometimes you can show that the problem is just too hard. And then you understood something really, really fundamental about, well, to me, the word. You might say it's just math, but like to me, all these questions are reflections or abstractions of the word. And the only way you can somehow sense the limits of what can and cannot be done, so you're not wasting your time indefinitely on trying to do things that cannot be done, is by thinking about whether something can be done. So that means that you're formulating this question of like, can this be computed in an efficient and effective way? And then you can try to get an answer, and sometimes the answer is going to be no. And then you know that you have to change your problem. So doing theory to a large degree is just thinking about these problems and the space of problems, like how the problems relate to each other. And along the way, you develop algorithms as well. If you're lucky, then you get positive answers, and then you want to have the algorithm in your hand. Sometimes you can prove that an algorithm exists, which is efficient and effective, without knowing that algorithm. That's sad, but it does happen. It did happen to me a couple of times. That you have tools to prove the existence of this algorithm without knowing what the algorithm is. That's weird, but it's not as lucky as being able to constructively write the algorithm. So oftentimes that's the ultimate goal. But because you just don't know whether this algorithm exists or not, and you might have asked a question that's too hard, your answer might be just no, that there is no algorithm with this properties. And so you should never assume that the answer could not be no, if it could be no, right? Like, unless you have some reasons to believe it, and that requires a proof. Anyway, so and then it becomes a game of, like thinking about how to change your problem so that now the problem is still realistic to the degree any of the things that we're talking about could be so to be realistic, but maybe an algorithm can address it, which is efficient and effective. So this is the game that I like to play, the game of doing research with theory. Okay. All right. So finally, some expectation management. So I think this is super important. So I expect that you take care of your own learning, and you're here to learn because you want to learn. And that's how I'm going to approach you as well. So you can expect me to respect you, respect your questions, help you to learn and grow, and try to understand your questions and teach you about the state of the art in RL. And if you have any concerns during the course about, either the contents or your learning or any behavior or whatnot, like, we are here and you can reach us, please speak up. And hopefully everyone is going to have a great time in the course. So normally, if it was in-person course, then I would see all the faces who would wave at each other and smile at each other. Sadly, that's not possible. And we would also introduce each other a bit briefly if we have so many people in the class, but know that we are online, this is a little bit harder. But we can still try. In the last 10 minutes, we don't really have, wait, okay, so I wanted to cover, oh, okay. Whoa, okay, so that's all right. I wanted to do this breakout room practice, but I guess maybe we're not going to do it. Like, it requires too much time. I would just maybe in the remaining 10 minutes, just talk very high level about reinforcement learning and the reinforcement learning problem, because you probably all want very badly to know about this. So to me, reinforcement learning is, again, a set of problems, interrelated problems. It's not a single problem. It's some blob of problems that you can change the characteristics of, and then you will see that we are defining many different problems within reinforcement learning. In particular, we're going to talk about this. Planning already came up, and you are interacting maybe with a simulator, and you want to come up with a good policy or good actions. And then online learning and batch learning, and like a lot of different variations of problems. It's also a body of knowledge and techniques and method, but primarily it's just like the types of problems and how they relate to each other. And the general area problem formulation, I try to come up with some way of defining that. So it has two parts. You're taking actions in a stochastic environment to maximize total reward by taking observations about the environment state. So there are a lot of things going on here. There's the word environment. So you think about maybe I don't know, you're developing a computer algorithm that is going to control a robot. And the robot needs to do something in the world. The world is the robot's environment in this case. Or it could be that you need to develop a control algorithm to, I don't know, order products for a warehouse. Okay, so then the actions that it takes is sending in orders or paying. The observation it makes is like whether the products arrive and how they leave. And you want to keep your stock at a certain level, but it's too expensive to use too much space and so on and so forth. So there are various considerations there. Or in a healthcare application, you're developing an algorithm that, I don't know, controls some medical device that helps a patient to, you know, be in an ideal state by taking measurements about their, I don't know, homeostasis, various biosignals. There's millions of these examples. So there is this environment, and we need to develop, we want to develop an algorithm that takes actions repeatedly to impact the state of the environment. The environment has a state. We're talking about this state as if it was like a truly well-defined thing, but there is a lot of I don't know, discussions going on about whether it's the right way to think about things by starting to think about states of the environments. I think that it doesn't really matter. I think you can, without loss of charity, just assume that the environment does have a state, as long as you're not assuming that you can access the state. If you start to assume that you can access the state, well, accessing the state on its own is not a problem because the history could always be the state. It becomes a problem if your algorithm would need to, you know, like see all the possible states or something crazy like that. That's impossible. So to a large degree, to me, the problem is not accessing the state. It's about how many states you have and whether your algorithm's runtime or whatever is going to scale detrimentally if you have a large number of states. So the other component here that was reward. So we want to give these systems a goal, and one simple way of defining what a goal is, just to assume that, well, along with every transition of the environment, so when there is a state and transition to next state in response to you taking action, there is a reward that is being incurred. So this is called the Markov reward. And this is quite powerful, but at the same time, it's not as powerful as some people would like it to be. So Rich really likes this reward hypothesis that that says that, well, you can rephrase every problem of interest in terms of a maximization problem like this. Well, okay, so there are mathematical limitations to this. You can easily come up with examples where you kind of just do things in such a way that this is just impossible. So if you have multiple signals that you care about, so that's like a practical example. So you care about, you know, I don't know, you're maybe an advertising company, so you want to make a lot of money, but maybe you also care about the well-being of your customers. So these two signals may be conflicting, right? And if you have this conflicting relationship, it's not so simple to express this as a single reward. You can actually show that a lot of, well, it's a very simple case is the optimal solution to this would be some stochastic policy. And if you had a single reward, then stochastic policies can always be replaced by deterministic policies. And since in this case, the original problem formulation, no deterministic policy is optimal. Deterministic policy would, you know, like always show this ad or that ad to the customer. It would never randomize. Okay, it's a little bit contrived, but because of this, it's this hypothesis that a single reward can summarize every possible goal, reasonable goal. I think it's just not true. But it's fine. I like to work with it nevertheless, right? And maybe even if it's not true, maybe you can reduce the other cases to this with some extra twists. And very often you can do that. So I think that it's a super useful framework despite its limitations. The reason I like it is because it's simple and clean. You have states, actions, stochastic transitions to next states, and the rewards along the transitions, just sum of the rewards. Maybe you apply a discounting. So that just means that future rewards were geometrically less than current rewards. You sum of the rewards, and then you just want to get a way of acting in the environment that maximizes these rewards. So I think it's a very nice, clean formulation. So why do we care about stochastic environments? I don't know. Maybe the reason is because there is this just a empirical observation that if you develop algorithms that are able to deal with stochastic words, then those algorithms tend to be more robust and more applicable, even if your conditions do not mean so. So some extra robustness is being sought for, but it's not clear that stochastic environments is a must. And in this course, we'll talk quite a bit about what is the price to be paid for assuming that the world is stochastic. It turns out that sometimes there is a non-trivial price to be paid for this. So you can make a problem impossibly hard by allowing stochastic transitions or stochastic rewards, whereas the corresponding deterministic problem with otherwise identical conditions could be, you know, polynomially solvable. So it's tractable versus an intractable problem just by switching from deterministics to stochastic or vice versa, right? So stochastic could really be much, much harder. But okay, so one reason to study this question is because it's interesting, right? To see that, wow, okay, like we are just like adding stochasticity and that makes the problem hard. Okay, that's good to know. It's provably hard. It's not just like we feel that it could be harder. It could be. In other cases, actually, there is no difference. So there are some conditions under which there is like you can solve the stochastic problem with a polynomial time algorithm with reasonable, I don't know, running times. Anyways, so sometimes it's good to just study some case because you're interested in, whether it's going too far or not. So, but I'm not convinced that stochasticity is a must-to-have property of environments. I'm not convinced about anything, but really open to change my mind. Okay, so learning. I'm going to ignore your question, Vlad. So learning. So what is learning? Learning means, well, learning is a vague concept. So here we are just trying to develop algorithms that take all the observations and then, like maybe have memory. So having a memory and changing memory, that's what learning is, right? But like how many algorithms exist which do not have memory? I'm like, okay, they are like, you can come up with some contrived cases, but most of the algorithms that we normally write do have memory. So it's like, there is nothing mythical about learning. Learning, it just means that you use memory in some way. And then sometimes here we use, I don't know, vectors and vector updates and whatnot. And it seems a little bit different because it's kind of numerical than your usual way of using memory, but it's just using memory. That's what learning is. I think the important thing about learning is that the algorithm needs to work across multiple environments, but that's also not different from the usual thing. When you develop an algorithm, it has to work across a whole range of inputs, like all matrices. You have your matrix multiplication have to be able to deal with all matrices. Maybe what's different is that if you write a matrix multiplication algorithm, you read in the whole matrix, both matrices actually, and then you multiply them. Here it's more like the streaming way, right? So when you're interacting with an environment, you kind of learn little bits about the environment. You don't see the whole environment, or you're interacting with a simulator of the environment, then you can poke the simulator in certain ways. So that's like gaining access to this object that you have to do the computation with in a bit by bit manner. So that's to me an integral part of learning. All right. So some possible questions you might ask: why this formulation? I think we discussed quite a bit about this, but you should be thinking a little bit more about this, like why this formulation. You might have other questions about what other formulations we could use. Okay, so we discussed a little bit why learning is important. Well, we didn't quite discuss why learning is important. I think that there is a special angle here for AI. So here maybe a reading assignment is to read Rich's beta lesson for AI. I think that's quite relevant for this discussion. Why we care about these learning algorithms, and then think about your own way of maybe phrasing that. Right, I'm over time, so maybe I just stop here because I want to respect people's time. We will start next time with MDPs. And by that time, maybe you're going to read about this. So in an MDP, you just have the states and actions, transitions. We already talked about it. And then there's going to be some questions about like what are these value functions. And you will see that in lecture notes, I'm very specific about that. I assume that there are finitely many states and finitely many actions. And then you should try to think about what would happen if I didn't make those assumptions. All right. Okay. So now I can answer Vlad's question. In which setting is stochastic version non-poly again? It's, I think, it's Q-star realizability. In Q-star realizability, online learning, deterministic deterministic problems, Jen Wang and Ben Van Roy have a polytime algorithm, and we prove an exponential lower bound for the stochastic version of the same problem, finite horizon setting. Yep. Okay.
That was the function approximation setting in online learning.
Yeah, that's
Yeah.
function approximation. Yeah.
Okay.
Yeah. All right.
But V-star realizability was polytime.
Yes.
So from like a learning perspective, does that mean we should somehow focus on V-star algorithms? Like, if we
No,
want.
V-star realizability, if you think about it, well, okay, this discussion is a little bit I think that it's maybe not interesting for everyone. Just to give the context, there are these two value functions, V star and Q star. And the V star only depends on the states, and the Q star depends on the states and actions. And somehow the Q star function helps you to act, and the V star function doesn't help you to act in the lack of extra knowledge. So V star is pretty useless unless you have a simulator. So that's the thing. So in the online setting, you have no choice. V star is useless.
Even if you have like an estimate of a simulator, so you have some models.
Yeah,
So-
but like then you have a simulator.
Oh, okay. So you're saying like you don't want to do if you don't want to do planning, then it's useless.
Yeah.
Okay.
And also that algorithm that you're referring to is not proven to be polytime. It has a polynomial query complexity, but the runtime we have no idea about. It's not really an algorithm.
Sorry. By runtime, do you mean like actual computation?
Compute cost.
Compute cost. Oh, okay. But like,
Yeah, it's all of this stuff comes up right away. All right. Any other questions? Maybe not as technical. Well, anyways, thanks for coming. The Slack channel is going to be open. If you're not on the Slack channel, then this is the time to write to your email, to your TAs, to be added to the Slack channel. Okay. All right. Thank you. See you next week.
Thank you.
Bye-bye.
Bye.
See you guys.